This talk is a little bit different than some of the talks you've seen here in the past. I'm going to be talking about a little bit of the history of how NASA has worked outside of the spheres of aeronautics in the past, and some of the opportunities going forward for how we can enhance the national infrastructure, specifically in rail. So the first question you're probably asking is, wait, isn't this an aerospace agency? Yes, it is, but we have an extensive history of working outside of aeronautics specifically. Great examples of this are the aerodynamic truck research in the 1970s, as well as several programs to enhance passenger rail throughout the 80s and 90s. There have been research on vehicles beyond trucks. We worked with the Ford Motor Company in the 90s, all the way up to the transport logistics of Amtrak's network in 2012. So we have an extensive history. I will step a little bit more detail into the aerodynamic truck research just as a great example of tech transfer coming out of the agency. This research started in the 1970s when a researcher at NASA Dryden was curious. There was also a gas crisis on. As to why American trucks were so unaerodynamic. And so they spent the next 20 years or so developing experiments and technologies to improve the aerodynamics and the safety of tractor trailers in the United States. They got several patents from it, including one for better airflow in cattle car trailers, which I've thought was a fun application of aeronautics. And their research can be seen in every tractor trailer you see on the road today, including the ever controversial Tesla semi there. So that's our history. What today says we should still be trying to work in areas outside aeronautics? First, in NASA's Authorization Act of 2017 and on and off several authorizations going into the past, it states that the administrator shall coordinate with other federal agencies and stakeholders on transportation research and innovation, including the Department of Transportation, whose purview is rail, trucking, etc. As well as in NASA's strategic plan, a heavy emphasis on innovative technologies with a focus on sustainable aviation. So what are the unsustainable areas of aviation today? Well, we have airport capacity issues. Slots are always a hot potato. We have a sustainable labor shortage with both controllers and pilots, leading to odd regional routes being served by 757s with very inconvenient schedules. The form factor of modern aircraft, as seats get tighter and tighter, have become less accessible for people with disabilities and anyone who is above the size of the average American as defined by the Department of Transportation. As well as, of course, a very high carbon footprint, especially when it comes to short-haul domestic flights. And this points to that NASA has got to consider some solutions outside of the aerospace bubble, specifically some of the solutions at the bottom of this carbon intensity chart, which is rail and international rail. So the gold example of rail in the world is Japan, and an excellent example relevant to the scales of regional transport in the United States is the Hokuriku Shinkansen, which travels from Tokyo to Kanazawa via Nagano and Toyama. It's about 2.5 to 3.1 hours, depending on how many stops it makes, and it's about a 250-mile long route. It opened in March 2015 as an extension of the Nagano Shinkansen, which opened in 1997, just prior to the Nagano Winter Olympics. The major route that was served by air prior to the opening of the Hokuriku Shinkansen was Tokyo Haneda to Toyama Airport. You can see Toyama Airport relative to the location of the rail route on the map here. Now, the route from Tokyo Haneda to Toyama Airport after the opening of the Shinkansen in the beginning of 2015 saw an 83% reduction in passenger volume that was directly moved over to the Shinkansen. Well, that brings up the question, wait, we're promoting air travel. We want better air travel. Isn't fewer passengers bad? Well, no. So a little bit of context. Tokyo has two airports, Narita and Haneda. Haneda is in the city center, and Narita is about 45 minutes out on express train. Now, it's much more convenient to take a flight from Haneda, but there are very limited slots. And a lot of those slots historically have been taken up by domestic connections to places like Toyama. But by removing the need to fly carbon intensive, low profitability domestic flights to these small regional airports, you have passengers fed into the air travel system via Shinkansen that are able to then fly on more profitable, more efficient long haul routes, particularly international routes. And we saw after the opening of the Hokuriku Shinkansen that several slots were opened up at Haneda, and the domestic airlines ANA and JAL were able to redirect those slots to profitable international flights that enhance the ability of Japan, a tourism-based economy, to bring in more revenue, as well as to make those airlines more sustainable, both per passenger mile and from a bottom line perspective. So that's why a well-developed transit infrastructure connected to air transport infrastructure can be a benefit to all parties involved. Your next possible question is, well, the US is just so big, that won't work here. Well, first of all, we have a lot of rail corridors. We spent 150 years building rail corridors in the United States, and most of them still exist and are still in service. Now, I'm not suggesting you should take a train from LA to New York, though that is a beautiful ride if you've got a week to kill and nowhere to be. But what's really of value is regional rail. And that is city pairs connected between 50 and 500 miles. That's the distance that research has shown is competitive both in time and cost with air travel. And that factors in door-to-door travel, the remote location of airports, security, boarding, all of that overhead that you've got with what would ostensibly be an hour-long flight. It becomes a 5-hour-long ordeal, and that's where the train comes in. So some of the corridors that are of interest to Amtrak today connect to major hub airports. The light blue lines and the yellow lines are areas where Amtrak wants to extend service going into 2030. Of particular interest is LA, Denver, Chicago, and Atlanta, major hub airports for the American airlines. If you can have passengers connecting into those hubs and onto your networks without having to expend resources and pilots on short haul hops, or as American has done in some routes locally, unreliable bus service, you improve the efficiency of the air network, you reduce the carbon footprint of that passenger's travel, and you increase the equity and accessibility of transport for every community along that route. So let's give you an example that's a little bit more close to home. We live in Hampton Roads, and the major metropolitan area of interest to us is the DC metro area. We are connected currently by the Amtrak Northeast Regional with a generous 2 trains a day. Yes, that was sarcastic, Bird. Now, if you took that service up to 1 to 2 hour frequency, regional rail between here and Richmond and here in DC, you enable connections to Richmond, Fredericksburg, Alexandria, DC, and destinations north with a low carbon footprint and an ease of access for the passenger. You also gain connections to Richmond Airport, which already is right next to the rail right of way. You just got to build a station. You get connection to Ronald Reagan Airport in DC via the Yellow Line, and now, after a long wait, Dulles via the MTA Silver Line, as well as connecting, again, every community in between to all of those metro areas and all of those economic opportunities beyond just the transport logistics. Now, there's some reasons why we don't have that today. Many of them are policy related, and I will not get into them today because legal told me not to. But some of those areas we can talk about are curvy rights of way that require active control of the vehicle to navigate its speed, weak bridges that require either replacement or reinforcement, as well as rolling stock on these routes that are 25 to 40 years old at best. Some of it's inherited when Amtrak was formed in the 1970s. And then, of course, there are signaling deficiencies managed by the operating railroad, CSX. That, again, is an issue for the Surface Transport Board. Today, we're going to address the top 2 points, which can be touched on by NASA technology. So the organization currently responsible for rail in the United States is the Federal Railway Administration. And their premier research organization is the Transportation Technology Center in Pueblo, Colorado. They have extensive test tracks, test tunnels, the ability to move trains around at various speeds and configurations to validate their performance. However, due to cost cutting in the 1980s, operation of this center was transferred to an organization run by the American Freight Railroads in 1982. Until 2022, they carried out essentially no research on efficient passenger rail for obvious reasons. However, in 2022, a research contractor, ENSCO, took over operation of the facility and is now refocusing on the national mandates for accessible, fast, and efficient passenger rail. However, because they are effectively a new organization rebuilding a capability, they've got excellent physical resources, but limited expertise in research and test. And that's where NASA can come into play. So we've got our sustainable aviation mandate. We've got a federal agency that needs help. What are some cross-cutting areas within NASA that are applicable to rail technology? Well, lightweight safety critical structures are a great one. Current American trains are about twice as heavy as their European and Japanese competitors. Of course, aerodynamics, drag, aeroacoustics, stability and control along curvy routes, passenger comfort and acoustics, operational automation, human-machine interface, the safety of railway crossings, the environmental impact of different modes and connections and acoustics. I could talk extensively on all of these points, but I'm going to spare you that. And unless you want to, over a drink another time, and focus just on one area of particular interest to me as a fluid dynamicist. And that's a phenomenon we call tunnel boom. So planes have sonic booms and high-speed trains have tunnel booms. This is essentially the canonical problem in compressible flow, the piston problem with some complexities. It's, I think, referred to as the leaky piston problem. So you can see on the bottom here a little diagram of that. Your train enters the tunnel at high speed and generates compression waves as the tunnel and the outer mode line of the train create an instantaneous or progressive compression. That creates a pressure wave you can see in black that propagates along the tunnel and steepens as it propagates, as you can see in the second line of that example. And that wave continues to steepen, and when it exits at the other end of the tunnel, far ahead of the train, it creates a sound very much akin to a sonic boom. Now, I'm going to play for you first the sound of a sonic boom from a NASA F/A-18, and then the sound of a tunnel boom from a German ICE-3 train. So listen carefully and see if you can spot which one is which. How many of you think the first one was the plane? And the second one? Well, it was the first one. The sounds are ostensibly identical. The giveaway was the crowd cheering for the aircraft and the deer running away from the train. Now, the aircraft example is, of course, NASA's X-59 low boom demonstrator, which you can see bears a striking similarity to the very long nose of JR East's Alpha X test train, which is being tested up to 420 km/h operations today. It's essentially a very similar problem to two areas we've been working at NASA for a long time. First, it bears a similarity to the supercritical airfoil, where you have a not necessarily supersonic compression over in a confined area, in this case, confined by the free stream or the tunnel, that creates a compressive effect that creates an adverse effect for the vehicle. And of course, the classic example is area ruling for drag reduction and the acoustics of supersonic aircraft. You can see a great example of that with Dick Whitcomb here at Langley, testing out that technique in the 1950s. It's now a staple of how we design aircraft, and it applies very directly to the problem of tunnel boom. So, how do you mitigate tunnel boom in practice? Well, there are a couple techniques. First, a longer nose, which you can see progressively longer noses in different Japanese Shinkansen above. And the length of the Alpha X test train is 22 meters long from its nose to its cab. However, the longer the nose of your head unit, the fewer passengers you can fit in it, and that's an operational constraint, as well as creating a complex geometry to mitigate that boom, has manufacturing limitations and operational limitations that have to be considered in a practical system. The German solution is tunnel portals, vented portals, where that initial compression is essentially distributed and weakened as the train enters the tunnel. However, topography around tunnels, particularly older tunnels, severely limit the ability to install these portals. A solution used by the Eurostar in the Channel Tunnel is to connect two different tunnels and have the pressure increase in one be vented to the other. However, it's a lot more expensive to build that kind of configuration than a single bore tunnel, and cost is king when it comes to public infrastructure. So NASA has capabilities that can address and improve each of these potential solutions to tunnel boom. We are a computational center of excellence. We have numerical codes that are best in class at handling compression wave and shock containing flows. We have experts in nonlinear acoustics, in acoustic liners, as well as the atmospheric propagation of compression waves and shock waves and how they affect the people and the environment exposed to them. That's a capability no one else in the United States has, and almost no one else in the world has, and it's directly applicable to this problem. Experimentally, and the area I care about most as an experimentalist, is of course the many wind tunnels, measurement capabilities, full-scale background-oriented Schlieren, you can see applied here to a T-38 jet, particle image velocimetry, as well as capability within our expertise to break a problem down as complex as tunnel boom, as complex as sonic boom, to a tractable fundamental physics problem that we can understand and then apply to the system. And that's an expertise that we are best in class at. Another area is, of course, the question, how do you build a complicated geometry that would reduce the boom of a vehicle? So on top, you can see the nose of one of the new W7 Shinkansens that operate on the Hokuriku route. This is handmade. There are craftsmen who hammer these panels into shape onto a form. There's some great videos on YouTube I recommend you check out of this process. The craftsmen describe that it takes 3 years just to understand how to loft the hammer, another 2 to understand how the metal responds to your hammer. And many of these craftsmen are not young. And that leads to advanced capabilities to manufacture weird shapes like those necessary for the X-59 out of composites using facilities like Isaac here at NASA Langley. There's also, again, an area of particular interest to me, opportunities for active flow control to both dynamically adjust the formation of those waves off of the train, but also attenuate them within the tunnel. And then, of course, we are able to better understand how booms affect people and wildlife and how they propagate around different topographies, what kind of liners or baffles would be helpful in mitigating these effects. That's an area we have extensive expertise in and continue to build on through the X-59 program. So some key takeaways I want you to know from today's talk, if you remember nothing else. Yes, we're an aerospace agency, but we have a history of working outside of aerospace, and we should continue to do so. Integrating regional rail into our national aerospace network is a critical step in a sustainable aviation future for the United States. We can help the Federal Railway Administration with our capabilities today. And there are a lot of cross-cutting problems within NASA that are funded, ready to go, and applicable to these problems. So I'd like you to think about what your area of expertise might apply, and what it would be like to be able to hop a fast, efficient, and quiet train from here to DC. So if you've got any thoughts or questions, I'd love to hear them now. Thank you for your attention.
So there's mics at each table. If you guys could go ahead and pass those along. Let you handle the questions.
Sure.
I'll let you know if there's questions.
Yep.
Hey, Louis. Interesting to think about the relative capabilities of high-speed rail in the U.S. versus in other countries, the examples of Europe and Japan you gave. Do you see NASA's abilities being better suited to solving some of these more complicated problems that currently deployed high-speed rail in other countries are facing, or to help make it more attractive to pursue high-speed rail here in the U.S.?
So I think it's both. So from the Japanese example, actually a French example, the current trains being built to replace the Acela trains running between DC and Boston are built by Alstom, originally for the TGV, the French high-speed train. They were supposed to go into operation this summer. They have not. And that's because the experience of Alstom in operating a train on a route, on a right-of-way like the Northeast Corridor that is twisty, old, and requires extensive geo-gated active control has proved to be a challenge. So there are technologies outside of the US, but there are peculiarities to American rail infrastructure that have to be adapted. And there's often not a financial motive for what are sustainable, often corporate rail operators in Europe and Asia to put the investment into making their technologies work on an American scale. So we have to essentially lead the effort in saying, yes, we could bring a Japanese train, a European train, but we're going to need to adapt it to our peculiarities. These are also problems that are still not fully answered overseas. The main limitation on speed on the Shinkansen network in the Tohoku Shinkansen, which is limited to 320 kilometers per hour right now, is tunnel boom. And that's why they're going to such extreme measures as this test train here. But their capabilities are less advanced than ours at understanding the formation and propagation of boom, both in the Japanese literature and the English literature. As well as, you know, you put the NASA stamp on something and suddenly it goes from, oh, it's just a train to, oh, it's the future. So there's a psychological benefit to that can help us prevent the US from getting into building more and more what's called gadget buns, or essentially not a train for the sake of not being a train. Any other questions? Yes. I'm going to pass her a mic. Push the button, make it green.
Yeah, thank you. Really nice presentation. And you've made a really good case. Like, you've sold me. I guess what are the next steps? Is there a petition I can sign, or is this actually gonna be part of NASA's mission?
I would love for anyone who has the power to make that so in this room. Help push this. My main purpose with this talk is to get people thinking about these applications and knowing that this is a today thing. This isn't a potential for tomorrow. And I won't just be the only person shouting in a corner, just build a train.
Yeah, my question is, I guess when you look at NASA delving into areas beyond our core mission, what comes to mind is that typically we do that by being paid by partners. They're going to pay us to help them. So, I mean, are there current eh, partnerships with Department of Transportation or front or other entities that are basically paying us to look into this problem?
So the primary short-term opportunity is through the Department of Transportation and the FRA. Um, Obviously, I am not part of the Strategic Partnerships Office, and I cannot speak to how the financial arrangements will go. But I think opening up a conversation between NASA, the FRA, and the Transportation Technology Center to see what are either non-reimbursable or things that bring funds into NASA, where we can go to them and say, hey, you need to understand the acoustics of your trains. We are experts in beamforming arrays. How can our expertise help you? They might, pay us for an array and the expertise to use it. That's the kind of thing that you would see. But that conversation has to happen before anyone can figure out if there is money to be moved around. I would also argue that there is an imperative to understanding how multimodal transport is. We can't just throw flying things in the middle of cities and expect it to be the most efficient, scalable way to do it. You can pack 500 people into a train. It's really hard to pack more than 4 people into an eVTOL right now. And scaling that beyond is a very difficult problem that I think it is important for NASA to step back and say, is this the appropriate, most efficient solution, the best use of the taxpayer dollar? And the answer isn't always going to be a thing that flies. To a man with a hammer, everything's a nail. To an aerospace engineer, everything has wings. And I think that's a modality that we should try and think outside of.
There's 2 online. David, you want to go first?
Sure, thanks. Yeah, I'm David Wagner. I work here at Langley, and I've been doing a lot of work with Convergent Aeronautics Solutions project. And right now, they're starting early exploration of a topic we're calling unconventional integration of aviation, and have already identified one of those possible integrations as being rail and aero.
Good to hear.
I'm wondering if you've heard of the project. Husni Idris, maybe he's kind of our subject matter expert in it right now. And
No,
if not, if you'd be interested in finding out more about it.
I am interested in finding more about it. I think the nature of communication across projects right now is that we don't hear about the cool stuff CAS does until it gets to a very terminal stage. So yes, I would like to learn more about that and be involved in that process.
Okay, great, thanks. I or someone from the team will send you an email then, if that's
Yep.
all right.
Please
Thank
do.
you very much.
Okay. I like terminal play on words there. Daniel.
Pun unintended.
So I love the presentation. I was just wondering, kind of along the same lines of some of the other questions, if you thought about taking this outside of the NASA bubble, like maybe a white paper, conference paper, talking to legislators, anything like
Yeah.
that.
Certainly, this is not the end of my advocacy for this field by any stretch. This is just a first venue, an internal venue to have this discussion and get people thinking. We as civil servants have limited abilities to talk to legislators about issues, but we can push the technical. We can, have talks at venues like SciTech and Aviation to say, hey, there's a different answer. And that's certainly something I hope others in this room may be inspired to do, and I certainly plan to do myself going forward.
It's really good to hear. Thanks.
Okay.
So you have three people from the acoustics branches here. Usually, yeah, well, there's a green light. Does that count?
Oh,
Should I hold it like this and
okay.
say, okay, cool.
Little further away. Your acoustics, you got this.
Yeah. So usually there are people who attend these from the Boom Group X-59 group and the liner group, and not today because you picked a day where there's actually two other things going on at the same time. I think we all came, well, I don't know much. I came because I didn't bring things for lunch. So I would be interested to know if you want to give this again.
I would
find some time.
Be happy to give this talk as many times as it takes.
Because
And I can certainly tailor it to that audience as well.
yeah, I didn't realize that it was going to be so acoustical.
Yes.
So I came here. I just like trains. So, but so I will ask a technical question. Is the pressure impulse that shocks up throughout the tunnel coming from when the train enters the tunnel, or is it coming from any time the train is going through the tunnel at a certain at or above a certain
It comes
speed?
from the entrance. That compression as the air in the tunnel kind of becomes like that leaky piston. It then propagates ahead of the train. There are some complexities with alternate shafts of the tunnel, expansion waves off of the inlet and the outlet that are beyond the scale of this talk, and I'd be happy to talk with you at length about. But it is primarily the entrance and then the exit from the tunnel that causes the effect.
But in concept, and maybe this is what's done operationally, if you enter the tunnel relatively slowly, then you can accelerate and go almost as fast as you want.
So the problem, unfortunately, is yes, that would be great. But so if you've got a really, really long tunnel, like an undersea tunnel, the faster you go, the faster you enter, you can also knock other vehicles off of opposing tracks, particularly in these single board tunnels. So that's another concern that has to do with more the bow of the vehicle in the tunnel. It's related to the physics of tunnel boom, but it's slightly different. And it's certainly a really cool and interesting area of research. I just didn't want this talk to take 3 hours.
Videos?
I think there are some good videos of Shinkansen passing freight trains in the Seikan Tunnel between Hokkaido and the main island of Japan, where you can see the containers kind of rattling around. And that is the big speed limit right now in that tunnel, is the ability for cooperation of freight and Shinkansen rail. So yes, there are a lot of really cool acoustic problems around trains, both in conventional travel within tunnels. Also, trains are cool. Thank you.
Let me switch back to do one online. Carolyn?
Thanks. This was a great talk. I really enjoyed it. I work remotely from the Boston area, and I have taken the Northeast Corridor rail service, Excella, ridden the Downeaster a bunch of times. A huge train enthusiast.
Excellent.
A huge problem that we have, however, has to do with scheduling and shared rails between freight and passenger. So frequently you run into problems in terms of trying to commute in this area. If you're doing a reverse commute, that the timing of the trains is terrible.
Yes.
And in talking with the conductors, the issues have to do with freight gets priority in terms of scheduling. And so your talk was really about the trains, but what the question I have with that context is, are there areas where NASA can contribute to better signals and automation of scheduling on the rails themselves to more
100%.
efficiently move people?
100%. That is an area that I think particularly SAC-D is got great experience in, is operational efficiencies, signaling. Our automation groups can be of great impact there. Again, and the disclaimer that was on the first slide, these are my opinions and not the opinion of the federal government. But the current issue with freight scheduling comes to the Surface Transport Board. The law as written gives passenger trains priority. However, that has not been enforced the entire time that law has been on the books. So I have many solutions to that problem that I would propose, but will propose in an unofficial setting.
Okay, thank you.
Hi. Yeah, I think my question's probably going to end up being quite similar to that previous one, but I was going to ask about in the long term whether you think that on-vehicle technologies or off-vehicle technologies in terms of the rail network will end up being more important and then also more or less feasible.
So in terms of feasibility, I think on-vehicle technologies is easier. It's easier to create a vehicle that's adapted to an existing corridor, both in terms of cost and the politics of large construction projects. I think for long-term sustainability of a system, upgrading the tracks, making trackside improvements like acoustic baffling, better sleepers, all of these things are the long-term way to do it. But it's going to take both. There's a theory in transport kind of called the minimum viable train. If you can get the minimum viable train running, you can prove to people that it's useful to them. And then they might not mind that more complicated construction project down the line. So if you start with on-vehicle technologies, you can then advocate for those infrastructural improvements like portal hoods, acoustic baffling, double tracking, the whole 9 yards.
Yeah, my name is Dave Helfrich, and had a couple questions for you. I work in SMA here at Langley, and you mentioned a couple things with respect to safety. And my question with respect to structural safety and the trade-offs required for both the design, lightening of the design. And the reason I'm asking that question is I remember from a number of years ago that there was a very bad,
Yes.
I think ICE German derailment where a number of trains were involved, or one train hitting embankment, that kind of thing. So I'm curious about that. And then as a second question, with respect to your exact problem that you were talking about here, how much effort has been going into, as you kind of alluded to, infrastructure as we build for the future, insofar as tunnel lining design? We're talking about optimizing maybe the structure or the design, aerodynamic design of the train itself, but what about also the tube that we're going through? Are there ways, are there maybe roughing of the tube itself that will help that? And as we build for the future, that impact is on those new construction projects, even though we may not be going fast, but planning for the future.
So I'll address your second question first. So yes, that is an area of research. One of, I think, the first kind of broken down physics problems that we can look at is how we can attenuate compression waves and shock waves in tubes, how we can redivert them or adjust their character, much like we do with the low boom. So that is a really important area of research. The extent which it has gone to in the international literature is mostly looking at whether you include gravel ballast or not within the tunnel. And it has been shown that the gravel ballast does attenuate the waves effectively as a roughness. But operationally, you don't want to have ballast in your tunnel because it can cause damage to your vehicles, and it can limit your speed through the tunnel by picking up aerodynamically that ballast in the confined space. So different linings on the tunnel, I think, will be a really cool application of NASA acoustics expertise. As for the first question, no form of transportation is 100% safe. And advancements in safety have been made in leaps and bounds, in particular with positive train control or active train control, where it is impossible for the operator of the train to overspeed the train, and computer vision that can detect issues at crossings, all things that I think are very much within how NASA treats autonomy as well, just in a slightly more one-dimensional space than we have for something like sense and avoid. As for structures, the current standards for structural both weight structure and testing of American rail vehicles was set in the 70s. Before we had advanced finite element analysis, before we had composites, before we had advanced aluminum alloys. And the FRA, because there has been no real research into it, has not updated those standards. And that's, I think, a great area that we can partner with the Transportation Technology Center on understanding how to safely improve the weight of these structures without compromising safety to the passengers, something that the Shinkansen network and the ICE network have done quite effectively.
Thank you very much for your answers. Wanted to just pass on, in case you're not aware, you probably are already aware, but you may want to make contact, because I think an organization that would be interested, very much interested in your presentation that you provided us today, might be someone like the Rail Passenger Association.
Yes.
And I don't know if you've contacted them, but they can initiate some advocacy for you.
I'm familiar with them. I haven't contacted them. I am tiptoeing around the restrictions I have as a civil servant to say things as NASA. So getting that go ahead internally to have those conversations with external groups like the Rail Passenger Association would be a first step. Thank you.
Any others in the room? Okay, Daniel, I think there's one more online.
Okay, so you mentioned not, or you think it makes sense to make like incremental steps, start with like the minimum viable, useful solution, and then just kind of build from there. Does that mean you don't think we should be making hyper leaps to solutions like the Hyperloop?
So the Hyperloop is, again, what we would call a gadget bun. It's neither financially or technically feasible. It's just cool because it's not a train. There are solutions that move people efficiently, fast, and safely in the world today that need some advocacy, some research to push them over the line in the United States. I would say making a big revolutionary leap from what is ostensibly 1970s rail technology to something like a maglev or a hyperloop would be run into the problem of being such a big task it would never happen. And you can look at that with the Chuo Shinkansen being built in Japan today, which is their first maglev line from Tokyo to Nagoya and on to Osaka. They have extensive experience with high-speed rail. They've been studying maglev technology for 40 years, and it is still a big cost and a big lift to get that line going. And I don't think the will in the United States is there to build a mega project on the scale of something like the Hyperloop, and the political will to put taxpayer dollars behind an unproven technology just because it's shiny and new is, I think, ill-founded.
Those are all really good points. The one thing I do like about it, though, is it actually gets people excited about public transportation, which is
And I think
hard to
that's
do.
the role NASA can play. Is when someone, the great tagline we had under J1 Shin in Aeronautics is "with you when you fly." It makes people excited about aviation when they can look at their plane and go, NASA did that. If you can look at the train and say NASA did that, you can gain a lot of that excitement that you get from the tech bros coming up with funny ideas.
Still, David.
Sure, thank you. Since we have a few minutes here, would you mind doing a little speculation as to what rail and air might look like 30 to 50 years out? That's kind of where CAS tries to operate.
Yeah.
And I noted your comment that you don't give much information out earlier in the process, and we're trying to work on that.
That's great. So I mean, the vision would be that every major airport in the United States is a multimodal hub. It is a rail station, both for intercity rail and local passenger rail, whether that be metro or commuter rail as we see it today, so that there is just low friction for a passenger going from a rural area where they might have an on-demand bus that would take them to their local train station, that would then connect them to a major airport. And that helps alleviate a lot of the equitability and access issues we see in the United States where rural communities are left behind. A lot of those rail corridors on that map I showed you run through rural communities. And a lot of those communities, the only transportation access they have is one train a day from Amtrak that probably shows up at midnight because it's running from Chicago to LA. So using rail as an integral part of our system so that a person anywhere in the country has access to the national airspace in a sustainable, equitable, and accessible way through multimodal hubs is kind of the vision I would like to see. And that is, that is something that exists in the Netherlands. It exists in France. It exists in Japan, and to a different extent, and again, lots of complexities to the application in China as well.
And you think we're headed in the right direction now? At least in general?
I think there is hope, particularly with recent infrastructure laws. Amtrak has put in orders for new train sets for the first time in 20, 30 years, and those will start being delivered later in the decade. So it's progress, and there is certainly, I think, a better understanding in Congress that rail has a place in the national infrastructure. But it, I think, is on us as civil servants to try and provide the technical expertise and resources that can further push that momentum.
Yeah, thank you very much. And hopefully fill in that map a little bit more.
Yes, yes.
30, 50 years out.
You left lots of time, so now we're going to ask a lot of questions,
Of
which
course.
is good. It's good. So actually, my question based on what you were just talking about is, the reality is that there's another aspect to this, which is the fact that the U.S. has like a car culture. We have tons of roads. And so, I guess I'm just pointing out that plays a big role in this too, right? So
Yeah.
the examples in Japan, like they already can go somewhere faster. So that's why they would pick to maybe take that over driving or they may have a different culture. So I guess I'm just asking, like you're talking about rural areas where there are already roads and maybe somebody can take a taxi to the rail, but I'm just,
So
what can
car
you say about
culture
that?
in the U.S. is complicated. First, I would say Japan is a titan in automotive manufacturing. And they are some of the most innovative and productive companies in the world. And they exist in both a successful domestic market alongside trains. So it shouldn't be well, if we build trains, then think of the American auto manufacturer. Now, as for the individual, we do have roads in a lot of places, and we built those at great government expense. And something that a lot of people say, well, this train looks so expensive. Your interstate was expensive. It was built before you noticed it. And so there has to be a cultural tweak from why would I take a train I could drive to why would I put up with traffic if I could take the train? And there are great taglines like "You are the traffic," and other things that can help push you. If you didn't have to commute to work driving, would you? We have car culture. No one is saying no one should ever drive a car ever again. Destroy car culture from the top down. We're saying that if you're taking a long road trip, if you're going somewhere that you commute to every day, is the best way for you and your community to do that an 8-lane strode cutting through your downtown core? And that's something the U.S. is starting to come to terms with. There have been great highway removal projects in recent years that have improved traffic and improved air quality and improved quality of life within those cities.